One evening in the spring of 1905, Albert Einstein, then a mere patent clerk in Bern, after trudging through his day's work, decided to board a tramcar on his way home. Einstein would often wrap up his work as soon as possible to contemplate the truths of the universe in his free time. It was one of these thought experiments he devised on that tramcar that revolutionized modern physics forever. While receding away from the Zeitglocke clock tower, Einstein imagined what would happen if the tramcar were receding at the speed of light. He realized that if he were to travel at 186,000 miles per second, the clock's hands would appear to completely freeze. At the same time, Einstein knew that, back at the clock tower, the hands would tick along at their normal pace. For Einstein, time had slowed down. This thought blew his mind. Einstein concluded that the faster you move through space, the slower you move through time. How is this possible? Einstein's work was heavily influenced by two of the most iconic physicists of all time. First, there were the laws of motion, discovered by his idol, Isaac Newton, and second were the laws of electromagnetism, laid down by James Clerk Maxwell. Newton's laws insisted that velocities are never absolute, but always relative, so that their magnitudes must be appended by the phrase, with respect to. For instance, a train travels at 40 kilometers per hour with respect to someone at rest. However, it only travels 20 kilometers per hour with respect to a train traveling 20 kilometers per hour in the same direction. Or, it travels 60 kilometers per hour with respect to another train traveling in the opposite direction at 20 kilometers per hour. This is also true for the velocities of Earth, the Sun, and the entire Milky Way galaxy. On the other hand, Maxwell found that the speed of an electromagnetic wave, such as light, is fixed at an exorbitant 299,792,458 meters per second, regardless of who observes it. However, Maxwell's notion seems incompatible with Newton's notion of relative velocities. If Newton's laws are truly universal, why should the speed of light be an exception? This presented Einstein with a daunting dilemma. This conflict between the ideas of Newton and Maxwell can be demonstrated with another of Einstein's brilliant thought experiments. Einstein imagined himself on a train platform witnessing two lightning bolts strike on either side of him. Now, because Einstein stands precisely in the middle of the two strikes, he receives the resulting beams of light from both sides at the same time. However, things get more complicated when someone on a passing train views this event while whizzing past Einstein at the speed of light. If the speed of light conforms to the rules of relativity, then the person on the train wouldn't witness the lightning strike simultaneously. Logically, the light closer to the man on the train would reach him first. A measurement of the speed of light made by both men would differ in magnitude. This would contradict an apparently fundamental truth of the universe. Einstein had to make a difficult choice. Either Newton's laws were incomplete, or the speed of light was not a universal constant. Einstein realized that the two notions could coexist with a small tweak in Newton's laws. To get rid of the discrepancy in the measurements, Einstein suggested that time itself, for the man on the train, must slow down to compensate for the decrease in speed, such that the magnitude remains a constant. Einstein called this absurdity time dilation, and his newfound theory special relativity. Newton believed that time moved unflinchingly in a single direction, forward. Einstein, however, had just realized that time stretches and contracts, varying with velocity. Due to its malleability, time, like space, deserved its own dimension. In fact, Einstein claimed that the two were one and the same. Together, they formed a four-dimensional fabric or continuum called space-time, upon which the mundane events of the universe would unfold. Einstein suggested that massive objects like the Sun didn't pull bodies like Earth with a mysterious, inexplicable tug, but rather curved the fabric of space-time around them, forcing Earth to fall down into this steep valley. A highly simplified analogy is the dip in a trampoline made by the of a bowling ball. If a marble were placed on that trampoline, the marble would immediately roll towards the bowling ball in the center. This is also true for Earth's gravity. We are pinned to the ground because space, so distorted by the Earth's mass, pushes us down from above. However, the slump in the fabric around Earth is not uniform, and Earth's gravity grows more intense as we move towards its center, where the curvature is at a maximum. Therefore, like the marble on the trampoline, an object that falls towards the Earth accelerates as it races towards the center of the planet. It falls faster when just above the surface than it does, say, when it is slightly above the atmosphere. But hey, according to special relativity, the faster you move through space, the slower you move through time. This means that time runs slower on Earth's surface than it does above the atmosphere. Now, because different planets have different masses, and thus different gravitational strengths, they also accelerate objects at different rates. As we have learned, this means a variable passage of time. This is what happens in the movie Interstellar, when the protagonists land on a planet in the proximity of a black hole. The gravity on the planet is so severe that 1 hour on the surface is equivalent to 7 years on Earth. To understand how motion affects time, let's consider the simplest timekeeping mechanism. A second passes each time the photon is reflected. Let's imagine two people, one in a spaceship slightly above Earth's atmosphere, and the second on top of a small hill just above the Earth's surface. Both are watching a man fall from space towards the ground. Let's say that the falling man is carrying the photon clock explained a moment ago. What do each of the two men observe as the man falls past them? What they observe is eerily similar to what a stationary person would observe when watching a ball bounce in a moving train. As the man falls from space, the light in his clock would appear to move in triangles to the two observers. This would mean that the light travels a longer distance, consequently stretching the duration of a second. It is obvious that the length of triangles the light traces, and therefore the duration of a second, is proportional to the velocity of the falling man. When we recall that objects closer to the center of the planet fall faster, we can determine that time would appear to pass slower to the man on the hill than it does to the man in the spaceship above. Of course, the difference is infinitesimal. The difference between the time measured by clocks at the tops of mountains and at the surface of Earth is a matter of nanoseconds. Time dilation affects every clock, whether it relies on basic electromagnetism or a complex combination of electromagnetism and Newton's laws of motion. In fact, even biological processes are slowed down. Yes, that's right. Your head is slightly older than your feet.